Cek. Assalamualaikum warahmatullahi wabarakatuh. Salam, Om Swastiastu, nama budaya, salam kebajikan, dan salam sejahtera bagi kita semua. Ladies and gentlemen, welcome to SEMAT X Kopi Sore Alumni Yandex Spesial Presentation Volcanic as Distribution Modeling. Good afternoon, everyone. Let me introduce myself. My name is Alina Bila Ramadhani from HMTG GEA ITB, class of 2021, who will be the host at the SEMAT X Kopi Sore Yandex Special Presentation Volcanic as Distribution Modeling. The seminar supported by Magister of Geology Engineering and Doktor Studi Program Institut Teknologi Bandung, HMTG GEA ITB, Graduate Association of Geological Engineering of Institut Teknologi Bandung, and Yandex. Support by IAGL West Java and Banten, IAGL for Education and Professional Development, SM-IAGI ITB, Association of Geology Engineering Student Program, Geology Tales and Institut Teknologi Bandung Geology Engineering Postgraduate Association. First of all, let's say thanks to Allah who has been gives us guidance, happiness, healthy, and mercy, so we can attend participation in this event. Before starting this, let's give praise and thanks to God Almighty, because by His grace we can carry out the SEMAT X Kopi Sore Alumni Event Yandex Special Presentation Volcanic as Distribution Modeling. This afternoon, let's also say pray so this activity can be carried out smoothly. Pray according to your respective religion beliefs. Pray never enough. Before entering the opening material session from Mas Mirzam, as head the Master and Doctor Study Program in Geology Engineering, time and place for Mas Mirzam to invite.
Thank you, Master Ceremony, for the opportunity to give a welcoming speech. Good afternoon, everyone. Good afternoon, Pak Edi, Bu Emi, Pak Hoiril, and our beloved student, and also for the valued guests who also joined from Zoom. This afternoon we have a webinar, as usually that every Friday afternoon we have a webinar especially for graduate students. So thank you for Mas Epo for your time, and also for Yandex. This afternoon we'll deliver about volcanic ash distribution modeling and the possibility between ITB and Yandex to have collaboration, and then also not only between ITB and also probably with CVGFN. So without further ado, I would like to thank once again on behalf of our department. Please enjoy the webinar, and hopefully we have fruitful discussion. Thank you very much.
Okay, good afternoon, ladies and gentlemen. My name is Fitra, and I will lead our webinar and discussion. And the topic is about future geological modeling, which we have some speakers. The first speakers is from Yandex. We have Ani, Dimitri, and Evgeny.
Evgeny.
Is Mr. Epo Kusumah from the student of doctoral degree in ITB. Okay. So we will begin the seminar, and I will let the Anna or Dimitri or Evgeny to present your information about the future of geological modeling. Okay. You can just present the slideshow.
Mm-hmm. Thank you so much. Thank you for this opportunity. We are really happy to be here with you today even in Zoom. We represent Russian technology company, Yandex, particularly Yandex Cloud platform. We are cloud services provider, one of the largest in Russia. And our team is responsible for a kind of social projects in ecology. And one of the projects we would like to to present today and would like to discuss with you in terms of possible cooperation is just a second. I will share slides. It's about neuronet and the volcanic ash. Here in Russia, we realized this project this year together with our data scientist Yandex school with students who realized make a model in the machine learning that predict the direction of volcanic ash after it was active. And first of all, we would like to present what kind of work was done, and Dmitry will tell you just some details in terms of machine learning, how it was realized step by step. Dmitry, just
thank you, Anna. This was a kind of research project in cooperation between Yandex Cloud, School of Data Analysis. So we used the help of the students from universities in Russia to work on the model for ash eruption detection. And also with Yandex Weather, because Yandex is a big company, it has a department that specifically works on predicting weather. And this was a joint project. So technically, the goal of the project was to predict how the ashes would propagate over several days from the eruption in Kamchatka. And we already have some infrastructure of cameras which observes about 13 volcanoes in Kamchatka. And so normally there would be a person sitting and watching the video. And as soon as eruption starts, like there were some manual predictions done on how the ash would propagate. So idea was to automate this. And this project, this implementation consisted from two big parts. First of all is the machine learning model to predict volcano eruption, not to predict, to detect volcano eruption from the camera, and to estimate the direction of eruption and the volume of ash distributed to the air. So this was a machine learning model that would predict this data from camera feed, video camera feed. And then the second part was to predict how the ash would propagate depending on those initial parameters, the volume of eruption and also the weather parameters like direction of wind, temperature, and so on. So the first part was specifically a project done by students to detect the eruption from camera. And there were a few problems in the implementation of this because, first of all, surprisingly, the data set was not big enough because eruptions do not happen very often. So there are not too many data points to train on. Secondly, the camera is fixed, so to train machine learning model on a small data set, we needed some form of data augmentation. So the one of the goals and challenges of the project was to come up with data augmentation model that would preserve the position of the camera view, but still augment the data in the way that machine learning model would be able to generalize better. So for this, they use some kind of color shifts algorithms to augment the data. And another problem, of course, is clouds, because clouds make it very easy to confuse volcano eruption like with clouds. And For that, they used like several frames. They feed several frames into the model. So basically, using a video feed from the past day to kind of see how the situation evolves, and doing some post filtering to avoid false positives. So this model, like first of all, the goal was to detect the volcano eruption and then to estimate the direction. For estimating the direction, basically, we employed classification model with several possible types of directions. And it was like 3 or 5 classes model, I think. And the accuracy, the F1 score of this model was around 70%. So we were able to relatively well predict the direction and the effect of volcano eruption. In terms of volume, there was also a regression model to estimate the volume, and that worked somehow. Well, because we don't know the correct value, it was also like several possible values for the ash volume, and there was a second model to predict the volume. Then this data was fed into the model of particle propagation, and for that we used open source project called LexPart, which is the like well-known project that deals specifically with this Lagrangian model for particle dispersion. And this model predicts the movement and the propagation of particles through air within the next day. Finally, all that was visualized on Yandex Maps. So this the data was put on top of the map using the Yandex Data Lens project for data visualization. So that basically allowed us to create the interface for end users who can just look at the map and see which regions in the map will be affected by the volcano eruption. So that is basically the overview. To train the model, so the main problems that we had is the set some clouds. So we used pre-trained image, and that was basically like pretty much straightforward. That's the overview.
We study with a dashboard and data the map. Just probably later I will send you in a few minutes the link. You could join and see the visualization how it looks like in a map. Probably some questions.
We'll have some discussion about this topic about us volcanic modeling, right? For the audience in Zoom meeting, you can raise hand if any question or any discussion to talk about. And for the audience in the room, you can speak directly in this room, and I will give you the microphone. Yeah. Okay. If any discussion or any question, just talk directly. Okay. So, Ellen from student in ITB.
Okay, thank you for this opportunity. Good afternoon. I'm Ellen Zeppelin. I'm a Master's Physical Engineering program here in ITB. And what I would like to ask is, what do you see as in the future? What kind of cooperation that you expect? And are there any expectations that you put in this like cooperation between Yandex and ITB? Thank you.
Okay, thank you so much. Thank you so much. We saw that there are lots of volcanoes in Indonesia, and it could be interested for you in terms of monitoring of their activities, possible cooperation with our team and probably research team to realize the same type of project with your local volcano to to teach your own model, probably together with our data scientist school, and to prove any scenario you want to prove, or probably also modeling or forecast or detecting and visualization on the map, just in terms of more accurate prediction of the movement of the ash.
I think there could be a good synergetic effect, because the more data we have, the better universal model for eruption detection we can train. And yeah, I think this project resulted in some expertise that we have in this problem of eruption detection, because there was some kind of research and different tests put into this project. So yeah, we can share the deeper insights into how this works, or try to train some larger model in cooperation.
Yeah, open for discussion and open for cooperation. Any ideas from your side will be appreciated. Thank you.
Okay, how is it, Ellen? Is it okay? So I want to ask too. So what the difference between this software with another software? Because we know that there are several software about the geological modeling, or especially in the distribution. What does the big difference between them?
I think here the main goal was to create the automated workflow for the whole process. So as I mentioned, we used the open source project for ash modeling as such. So we did not invent like this part ourselves, but we put it into in the context of larger system, which would create for the end user a friendly interface with the map, and which would automate like this whole process. So from eruption detection to modeling to the final visualization. So this was all done in the cloud. So this cloud system, I think, is the main goal of the project.
Okay, thank you, Mr. Dimitri. And Mr. Asep, you want to ask or not?
Yes, thank you. Good evening, Miss Anna, Mr. Dimitri, and all. Let me introduce myself. My name is Asep Saipulo. So I'm the head of Geological Engineering Study Program. So we are happy that a couple weeks ago some colleagues from Yandex come to our campus. We are happy. So and then from that meeting, so we want to know more detail about your program, because at that moment that Yandex told that the equipment is only camera. So it's quite rare in our case. So of course we have a camera in the volcanoes, but using only camera to detect the distribution of the ash is probably quite difficult. So that's why we want to more detail. How could you get kind of the 2 or 3 dimensional directions of the ash, probably only using one static camera. So, but unfortunately, I didn't see any slide or
Yeah, we just
And,
wasn't prepared for presentation in reality because we thought it will be a small discussion peer to peer. So very sorry for this kind of misunderstanding. We will provide all the details regarding the visualization, but I think Dmitry could answer why we used only cameras because yeah, Dmitry, regarding
Yeah,
the
I think
data.
the main reason we used only cameras is because we already had cameras monitoring a set of volcanoes, and we wanted to come up with some way of predicting ash distribution from this source. So we, of course, this model would be less accurate comparing to other approaches. For example, if we had LiDAR 3D cameras, or if we had several cameras monitoring one volcano, that would allow much better predictions. And I think that is one of the possible ways to improve this, is to have several cameras, which would allow estimating kind of 3D shape of volcano eruption. But in our project, we had just one camera, so we wanted to estimate the initial parameters for monitoring from this video feed. The main part in the distribution, of course, is played by weather parameters like wind, wind direction, and so on. So we also took, of course, this into account. And if we are talking about ash distribution within like 1 day after the eruption, that is like the more important than initial direction. So that's why we can allow ourselves some kind of inaccuracy in predicting the initial direction of volcano eruption. But by having fixed camera, so we know how the camera is fixed, we know the distance, and this allows us from the image to estimate the amount of ash and roughly the direction. That's, I think.
okay, maybe in the next step, if we want to go to the collaboration, so probably if there is any specific, I mean, how this work? That's the main question actually. But okay, it's maybe for this moment it's okay. So for collaboration, so we are welcome actually. So we are welcome. We are very welcome if you propose to kind of the collaboration. So there are some steps we have to do in our faculty in our campus, how to deal with the international collaborations. But it's a good opportunity, I think, for us also, how we can utilize our observations using your model. So of course, you also will have a kind of benefit that for accessing some data in Indonesia for volcanoes. So it's easier through university actually. So maybe next opportunity, more detailed presentations about how this model can work. So maybe it's better, Anna.
Probably even not a presentation, but just demo. We could provide access
Yes.
that you could yourself just to try to choose the volcano to see the focused how it's going on, and it will be more visual. Yeah.
Yes, it's good.
Thank you.
So, and also point by point, what kind of the collaborations we will go to in the next. So we had discussed before.
Okay. Thank you so much.
Okay, thank you, Anna.
Thank you.
Thank you.
And here we have Mr. Andri Subandrio. Please tell your question.
Hello. Good
I
evening,
hear you.
Anna and Dimitri. Hello. I am Andri Subandrio. I am geologist, also from ITB. So I am also economic geologist, naturally. Yeah. So I have asked about what kind of camera is it? Maybe like Mr. Asep, the question. Yeah. If I have looked your presentation about the distribution of ash maybe you look from a satellite. Is it like a satellite or drone? So it's look like from the air. Yeah, it is maybe the camera is complete with the uh, with multispectral maybe. Yeah, it is a multispectral camera on this mitigation for S cloud. Thank you.
In this project, we use the normal camera and the side view on volcano, so it's not a satellite. It's basically like a side view. And from one side, as I mentioned, it's difficult to estimate the total amount of ash because we just only see one side, and the cloud can be like of different shapes. So ideally, we were targeting the situation when there would be like several normal cameras overseeing the volcano. Not a satellite because it's probably not.
But the satellite we use for weather forecasts. So we have, so we have because we have the second model from our weather team, and they use satellite pictures for weather forecasts.
Sorry, is that only visible camera, visible light camera, or multispectral with infrared or maybe with the
multispectral?
Yeah, multispectral. Okay.
Multispectral.
Yeah,
and we also have plans to use Internet of Things, use different types of equipment for tagging. Yeah.
Yeah, actually, the more data we have, the better results we can get. So integrating different data sources would definitely be a very interesting story. At the moment, this was kind of pilot project, so we wanted to demonstrate what we can get from the equipment which is already there, which is already available.
Thank you very much.
So,
thank you.
Program in the software, it could be estimate the volume or the distribution, the spreading of the volcanic ash. Is it true? One camera or several camera?
The volume, you mean the volume and also the level of distribution.
Okay, is there any discussion again from this room or the online meeting? Okay.
We will be happy to answer all other questions probably in a written form or just to provide some materials, I mean, presentation.
Okay, thank you, Anna and Dimitri and Evgeny. So I think
thank you.
If any question or any discussion about this topic, you can contact the Mr. and the Miss here, and then we can give some contact maybe if possible. And because there is not any question again, so we will continue the seminar with
thank you,
Mr. Epo from the doctoral degree student in ITB. Okay. So we will enjoy the presentation from the Mr. Epo. Okay, thank you for the Mr. Dimitri, Miss Anna, and Mr. Evgeny for the chance in this webinar. Thank you. Okay, this is some profile from Mr. Epo Kusumah. Maybe it's really small, but I can read that. So the education for Mr. Epo is begin with the geological engineering bachelor degree in ITB. Then after that, he have graduated from University of Manchester in petroleum geoscience, and now become the student in geological engineering doctoral degree in ITB. And for the professional experience, you have some experience like junior geologist in Vika Indonesia, lecturer in Pertamina University, and founders of Setstrat. Setstrat is the application software, right? Oh, okay. Okay. After that, we will have a presentation for Mr. Epo, because if we want to read all about this profile, it will take a longer time. So give an applause for the Mr. Epo. Okay. All right. Good afternoon, everyone. Should I speak in Indonesia or English? I think since I were introduced with English, then I will continue my presentation with English too. Okay, allow me to introduce myself. My name is Epo P. Kusumah. I'm a current student in ITB in doctoral program. And at this moment, I would like to give a little bit presentation, an outline about what is forward modeling in geology, and some part of it is become my current doctoral degree research planning. Okay, in this so in this opportunity, I would like to give a brief introduction on what is forward modeling all about, and how is it important in geology and everything else. So why do I do forward modeling in geology? Maybe some of you already familiar with this kind of cross-section. We have seismic cross-section, we have reflector, and we geology likes to draw interpretation in it, okay? What we see here, we have like these red lines that represent sequence boundary, and the yellow area that we think it is a sandstone because it's the top set of delta. The green area is a shale that we think is a pro-delta part of the delta. But are we really sure about it? There is no well has been drilled in here, all right? So because there is no well, we cannot validate it, okay? So there are uncertainty present in this kind of interpretation, because what we think it is a sand, it might not really a sand, because it has not been proven, right? So we need another things to this kind of things. Because of this image, because of this kind of interpretations, it pushes me to do something really different with the other people. So I was thinking about the process in geology that can be replicated by computation process. So by forward modeling, it is possible for us to have more justification on what is inside that kind of package of sediment. Whether we're going to have a sand or shale or something like that, and why do we have, so according to this seismic, we see that there are a little bit of transgressive system track in that kind of blue thin layer. We don't really know what kind of lithology is it, and we don't really have any justification of what it is inside. So with forward modeling, it is possible for us to give a little bit argument about what is inside that kind of package of sediment. So we're going to see and how it works later, but in general, I'd like to give a brief introduction about forward modeling. So what is forward modeling? Forward modeling is a computation process that allows us to simulate the geological process. So instead of, maybe some of you are already familiar with the term geological modeling, yeah? So we create a geological model.
In the past, we tried to draw the geological object inside the 3D grid or maybe 2D map or something like that. So we draw that by using our interpretation. Using forward modeling, instead of we drawing it, we just giving them a physical property of the rocks, and then we apply stresses. We apply some physical process that allow us to allow the system to replicate what is the physical process all about, and we will be able to see the geological phenomena that occur because of that kind of physics process. So it's not like typical geological modeling that we draw the object, but instead here we just apply physics in it, and we'll see what are the response of the particle. So actually, forward modeling can be differentiated into. We have the analog forward modeling and the computation-based forward modeling. So the analog forward modeling, or maybe, yeah, the analog forward modeling, just like what Mr. Benjamin Sapi already done. We're doing sandbox. Sandbox is a kind of forward modeling, but it is analog one. Other than sandbox, we do also have like fake delta, yeah. Desktop delta is like showing us the progression of the delta or something like that using a small tools, something like that. So that's kind of tools give us a bit of insight of what's going on the geological object when we apply stress or something like that. In this opportunity, I would like to give a presentation about what is forward modeling in computation realms and what it's all about. Yeah. So in general, when we are trying to do forward modeling, there are 4 things that is very important. The first one is time discretization. So what is time discretization? Is like when you're doing forward modeling, we will introduce time dimension in our model. Yeah. So the time will affect how the things works from time to time, things like that, and it also controls how physics work in our system. And then we do also have to define the initial condition. The initial condition is like before it was deformed. For example, if you would like to doing for modeling in sandbox, before it deformed, it should look like what. And then boundary condition is like the parameters that will be happen when things happen. For example, like when we have 2 particles colliding, what will happen to the simulation and something like that. That boundary condition is also called rule in forward modeling. And the other part is, of course, visualization, because without visualization, it is very hard for us to understand. So what I mean by initial condition is like this one. I will give you a brief introduction what is forward modeling all about. So this is a forward modeling about 2 particles or 2 balls that moving around. Yeah. So this is the initial condition. Okay. With this kind of initial condition, initial condition were defined not only by the position but also the property of each particle. So for each particle, it will have velocity and then have acceleration, mass, elasticity, friction, and everything else. Yeah, and also mention about the time step. Yeah, and when we talking about time discretization, time step. This is the time one. Since we have velocity, then the particle will move to other position because of every single particle have velocity. Yeah, the initial condition. So the velocity, the location, the acceleration, and everything else will be updated from time to time. Yeah, and those time step is called time discretization. The time discretization also can be modified, whether we're going to have like very rough time step or very fine time step. It will be determine whether our modeling will be very smooth or not. So this is what will happen if we have like 3 time steps. Time 0, time 1, time 2, time 3. So in geological object, it will be very complex, much more complex than this. Yeah, we're going to use like tens of thousands of particles, and we're going to have like a lot of parameters for each particle. And this is the things that I want to point out first. Like, why do we forward modeling? The first is like, well, it has a lot of potential. Okay, yet nobody really, no many people are doing this kind of research, especially in Indonesia. And other things, it's like it's very interesting topics ya. Jadi at the moment, computation is like very cheap and everyone can do it in their laptop. And I think it is very good if we have this kind of for modeling for everyone. However, it comes also with challenge. For modeling is very wide, as you know, that it's just like the main in computation science. Yeah, it's not only applicable in geology but also in other subjects. And for geology, for modeling also divided into several types of for modeling. For example, like we have particle based, physical based, geometric based, and everything else. And at the moment, even though for modeling have a lot of potential, there are not many tools in the market at the moment that used for modeling. At the moment, we have BASIC and we have Project, but you know it is expensive and need a lot of computation power. So another like the challenge is acceptability of this method. This method is very new, okay? Because it's new, not really many people understand what on using modeling, and yeah, because it's new, it is very hard to enter the market, something like that. Even in the science community, it is very hard to convince people that this is good and it is applicable for geology. So yeah, for modeling has been carried out in many years ago. The one that I talk about is this Peter Burgess is doing research in numerical modeling in geology, and he started this kind of for modeling in 1996, and it's been around for like decades. And you know, at the moment there are more sophisticated methods. However, it's not on the market because what? Because yeah, developers not ready to use that kind of things. So for modeling can be used for structural, basin modeling, sequence stratigraphy, and mineralogy, and everything else actually. And in general, we have two types of forward modeling. The first is like the real forward modeling. It's called process-based forward modeling, and the second one is the geometric-based forward modeling. Forward modeling that using physics, it really govern physics process like Newtonian particle collision, particle interaction, and then viscosity and elasticity and everything else. Everything is govern that kind of thing. And the other one is like for modeling that use geometry instead of process. So the geometry is really easy to use and very intuitive. However, the accuracy is not very good because you know that sometimes physics really defines the geometry of the things that being formed in geology. And as we talk about forward modeling, we can also classify forward modeling into two types. The first one is the analog kind of forward modeling that we just like sandbox and everything else, and computer based. And when we are talking about computer based, there are three kinds of forward modeling also. The first one is like DEM, or we call discrete element modeling forward modeling, and then grid based and geometric based that we're going to talk about more today. And this is the key differences between discrete element modeling and finite element modeling. Discrete element modeling is forward modeling that assumes that Earth object consists of particles just like what we saw on the screen, and every single particle will interact one to the other, and all those interaction will govern by physics law. Yeah, and the other one is finite element modeling. Object is composed of grid. Every single simulation have their own weakness and strength, but I prefer to use a discrete element model. So this is discrete element modeling that I developed. Oh, sorry. Yeah, actually it works. well, it actually works, but it works really slowly. So as we can see that every single part of this basin will be assumed as a particle, and every single particle interacting one to the others. And once we press this boundary on the left, all the particles will be interacting, and everything is governed by physics. As we can see here that, yeah, this kind of sandbox simulation form some kind of folding. However, there are a lot of things that we need to learn about in this kind of simulation. So we shall continue. Other than sandbox simulation, we can also see that this kind of simulation can also be used to simulate how the tectonic collision works. Yeah. So this is the red one. I presume that this is the Australian plates, and the green one is I don't know, maybe Sunda plates, and this is how they meet each other. And I don't know, just thinking about maybe we can collide them together, and we see what kind of basin we're going to form when we collide them to one to the others, right? Something like that, yes. Well, as I mentioned before, that for modeling have a lot of potential. However, it is very hard for people to understand, because you need to understand the first computation methods, and then the physics methods, and then how to optimize everything, and also the geological aspect one. Yeah, this is the forward modeling that we for sequence stratigraphy. We use a geometrical approach. So what we're doing here is try to replicate for what Peter Burgess has been done in 1996 in his first paper about forward modeling. So this is kind of forward modeling that were being introduced at the beginning of forward modeling, and it is very interesting. It's very simple yet have a really good result. So what does the geometrical based forward modeling do is try to replicate what the Earth's doing in terms of geometry, and then replicate the process again. So just like this one, we see we have the delta here. Okay, we observe when we have the delta is like moving toward the sea, yeah. So it's like prograding. And if we grow how the process occur, it's just like this. So we have two packages here. The first packages is like the one on the left, and the other one is to the right. So what, according to the observation, we can see that every single package have their own geometry, and the geometry were governed by the sea level, and then the initial slope, and then the initial and previous sediment being deposited. So we have this kind of things that we call as principal geometry. So this kind of principal geometry be repeated over and over again in order for us to replicate how the sediment being sedimented in the basin. Yeah. Of course, there are a lot of things that we need to consider when we are trying to simulate this kind of things. The first is like the sea level, and then the supply of sediment and everything else. That kind of thing that we can model using the forward modeling, because we don't have, I mean, like, in order to replicate this process, we need to set up a delta like this, which not everyone have this kind of things, yeah. Very complicated, it's wet, and you know, everything can have things like very complicated, yeah. But if we are using this kind of thing, it will replace, or maybe not replace, like have the same level of insight that we get from the desktop delta that what has been presented before. And how does these things work? First, we need to find the X and Y location of the shoreline according to the geometry. And then once we get the shoreline, we need to draw the initial deposition node. Yeah. And then once we get that, we can now draw the initial dip against the slope, and then move the slope away from this line toward the sea. As we see, move this line that formed by the sea level and then the slope, will have this orange area, the yellow area. this area, yellow area will have area ya, what is it, luas area gitu. And then we can repeat the process again and again. So the first, for example, like the bounding condition is like we're going to make a depositional area about 600, and then for the next one we can also for example, like this is the first package we have, and we're going to replicate this kind of package on the next one. But you know, as we try to create another package, the geometry is changing, yeah. So we have to consider the geometry or geometry parameter that we're going to form on the second package here, right? So the first one and the second one, the only constraint that we use to do this kind of forward modeling is the area. So the first area and the second area have to have the same area. For example, like this one have area of 600 meters square or something like that in this 2D plane, and the second area have to have the same area as well, 600 meters square. However, because the shape is changing, as you see here, the depth is deeper on the right one, so the geometry will be different. So in order to tackle that kind of problem, we need to introduce a little bit of machine learning here. So we use the machine learning to optimize to find the geometry that fits on the forward modeling, things like that. And yeah, long short story, this is the end result. So as you can see here, the sea level is rising and drop and rising and drop, and we can see that we have several stages of sediment, and every single sediment will represented by the color here. The yellow color represent the sediment that being deposited on the shallower area, and the green one and dark one is the sediment that being deposited in deeper area. So you can see here that if we have the oscillation of sea level over here, we expect to have several packages of sediment, several packages of sandstone that were separated by several stringers of shale over here. So does it really answer my questions on the I think it did, because in the first slide I don't really know what kind of lithology it is, and I don't really have any justification. But with this, I have another justification to tell the audience or the of the day whether this is sand or shale or something like that. And we can also create the simulation a little bit more complex. For example, like this, where the sea level doesn't follow the sinusoid. Yeah. This data is gathered from a gamma ray curve that collected from well, and this is the result. It is very interesting to see how the sediment being scattered because the change of sea level. So this is how it's done. And we can also introduce a little bit more complexity. For example, like we add a fault during deposition. As we all know that sometimes we can also have faults during depositions, yeah. And this kind of model, this kind of forward modeling can also implement faults during deposition. So we can, it is possible for us to replicate what we call growth depositional setting and something like that. And yeah, this is how it looks like in the sediment package. Whether is it correct or not, we don't know, because still this is a research in progress, and unfortunately in Indonesia it's only me who doing this kind of thing. So I'm kind of short in hand. If there are people who are interested in doing this kind of thing, please don't hesitate, just call. Okay. Next, we also have a forward modeling that using physics instead of geometry. This one has been presented before, and there are two kind of physics-based forward modeling. The first one is particle-based, and the second one is the grid-based. Every single of it have their own pros and cons. I prefer DEM because it's much more fixed and it's gradable. every single particle is loose, and we can form faults easily by using DEM. And we can also aggregate several particles in order to behave like solid particles, something like that. In other words, we have flexibility. But although it is very flexible and very good, it is very computational heavy because it requires a lot of computation. Other than that, we do also have FEM. I don't really say that if FEM is bad. It's just good for another purpose. Yeah. For example, like if we have geothermal system, we can model the heat dissipation better by using FEM instead of DEM. And we do also, you know, when we are talking about basin being produced, I mean, like if you have hydrological basin and we produce water so much, the basin will be sagging, right? And it is very easy. It is very easy to, not very easy. It is better for us to model that kind of thing by using FEM. So this is FEM. As you can see here, everything is grid based, and this is DEM, where everything is grid based, particle based, where in the where every single geological object will be treated as particle, and for every single particle we can adjust its parameter like elasticity, frictions, particle size, and everything else. Yeah, and this is the things that I have been presented in the image Houston 2023. I'm trying to simulate the form by using discrete element modeling. Fortunately, it's good, and the thing about this forward modeling is that it's not only can be used for one movement like extensional, but we can also invert the process. So we can also simulate the basin inversion and scene inversion filling by using this kind of methods, which has never been done by people. So what is physics based? So yeah, as I mentioned before, thing is particle, and particle have properties. So we can also play ping pong, this kind of ping pong with this kind of algorithm. If we have one particle and we fall it, we hang it and then we free fall the ball, it will bounces, and the bounces of the ball of the particle depends on its elasticity property. Yeah, and then if we have like a slope, and then we put balls there, it will be rolling and everything else. That's just physics. Yeah. If you are familiar with the game, what we call Angry Birds, this kind of engine is the same with Angry Birds. Yeah. So this kind of particle, when they are colliding with the other, they will calculate the momentum, rotations, kinematics, energy, and anything else. And that's what's amazing about this kind of method, because when we are modeling, we can see the strain, but it is hard for us to calculate the stress. But with this, it is possible for us to estimate the stress, although it is not very accurate, I think. So yeah, other than particle collisions, things like critical angle and then friction coefficient, everything else will also become one of the parameters of the particle. So because it inherits coefficient friction properties for particle, it also follows the Moore criterion failure, something like that. So the degree, or the what is it? If we try to form a rock and then we deform it, it will create the and the angle factors will be determined by the properties that we have for the particle. So for example, like this one, I try to simulate the formation of the rocks with the friction coefficient 0.2. I presume this is a shell, and if we break the shell, it forms this deformation style. I don't know whether is it right or not. This is my very first attempt to do this. And then if we change the material into friction 0.65, the deformation style also will change. So the angle will be a bit more steeper. And then we change also with 0.95. I don't know whether it's any rock have friction of 0.95. It also have different style of deformation. Yeah, it is a little bit more steep. So according to my simulation and calculation manually, I can see that the degree of the deformation is different from one to the others, where if we increase the mu or friction coefficient, the angle of the deformation or the fracture, it is a little bit more steep, yeah. And why do I do this instead of the sandbox? Because at the beginning, my aim is to do the sandbox modeling, because we're talking about earth material, whether is it in the sandbox, in the basin, whether is it in the container that we press, everything will behave according to physics. And the physics that we're talking about is this kind of Moore diagram. So, and a Moore will be governed by the friction coefficient, things like that. And yeah, that's how it works. And then once we are confident, anyway, this kind of research is still ongoing. So there is a little bit of inaccuracy. Why? Because the number of degree and then number, as you can see that the friction number of 0.9 and then 0.65 is almost the same. It's supposed to be different though, because of its inaccuracy. I still have a lot of homeworks with this kind of thing. Yeah, Pak Benjamin. And then try it also with this kind of deformation. If we have this kind of sandbox and we press it, this one using the friction coefficient of 0.65, then we have this kind of deformations. Does it look realistic? Well, there are a lot of things that we need to work at. For example, like we have foldings here, but we do also we do also have a lot of micro foldings inside the folding. Does it realistic? I don't know. We need to discuss about this more later. And then we can also change the friction coefficient from 0.6 into 0.2. And what is interesting is like, well, the deformation style is quite different. This part is quite the same, but later part be a bit different because of the loading, I think. So just try to growing underneath the loading above. And as you can see, it's forming some kind of detachment, but I don't know whether is it right or not. And then as we increase the sediment thickness, the behavior of the deformation is also changing. There are a lot of things that we need to work on this kind of experiment. However, for my research, I will try to focus on the basic things, and then like thin sediment with ramp or something like that, or maybe something a little bit more principle, like doing axial test or something like that. Okay. Actually, for this kind of research simulation, we can also make this simulation a little bit more complex. For example, like in here we have a flat basalt, yeah, a flat basalt where the base of this sandbox is like flat. We can also playing around with the shape of the base, and we can also move the base upward or vertically, yeah, upward or downward, or maybe we can create a extensional inside the basin, and we can also revert the process. For example, this is compressional, and then we try to extend it, and what does it looks like? That's what make it good. I mean, not good. What's make it more interesting about for modeling, because we can implement a lot of scenario, whether is it simple or complex. Then we will be able to estimate what kind of geological deformation that we have, geological phenomena that we have, something like that. So actually there are one more for modeling that I would like to show, but unfortunately it's on my laptop, and this kind of display cannot be connected with my laptop. And yeah, it is for modeling about how the river, how do the river meandering, and it evolves from time to time. And I think it will be good for us to use it in order to make reservoir modeling in the future, maybe. So in conclusion, for modeling for me is it have a lot of room to improve. Yeah, we have to really working on the accuracy and the optimization of how the simulation working, and you know there are a lot of research have to be done, and we need new generation to work on it, I think. Yeah, and it can be implemented in many aspects of geology, sandbox, and then as what is it, delta, mineral, and everything else. And the challenges, of course, there are challenges. The challenges, I think, what is the most challenging is like how to convince people that is not really familiar with computation, tell them that this is important and this is relevant with geology. I think that's all my presentation. I would like to welcome any questions if there's any.
Okay, thank you so much for Mr. Epo for the presentation. It's so cool and it's so interesting for me, and I think also the audience, because the forward modeling is so rare in Indonesian, and you have do this kind of study and make some software from this using machine learning, using geological and physical properties to estimate how the geological event influenced by also all of the parameters in a realistic event. And so about this kind of modeling using about the discrete element modeling or finite element modeling, discrete element, and then about this modeling can use to sedimentation, and then about the deformation of the rock basin, and then many even of geological too. So we have some discussion time. If you all want to ask to Mr. Epo about this kind of modeling, forward modeling, and then if some on the online meeting want to ask to just raise hand using Zoom feature. Okay, in this room, you have the question, maybe from the oil man, from the APG man in behind, or the lecturer. Just please have a question. So first, I want to ask about your experience about this modeling, and do you ever do this forward modeling in real place, maybe in Indonesia or somewhere, and how the compatibility between the software and compared to the modeling in your software, because it's like some sandbox digital, right? And how the compatibility between the software and then the real event.
I have very short answer. I have never implemented this in a real scenario, so this is part of my research and this is part of my journey. So it will be my first time, I think, to implement this kind of real world scenario, whether comparing the sandbox with for modeling, the seismic cross section with for modeling, everything else, it will be my first time. I was thinking about implement these kind of things in my future projects in Glagaria, but I don't know whether is it compatible or not. It's just part of research.
Okay, thank you so much, Mr. Epo. So it is interesting for us for the master degree or the bachelor degree. If you want to join the Mr. Epo study about this modeling, maybe you can go to the some basin, and then to okay, to join about this modeling and just compare about the reality. Is it okay, or maybe we have to change some parameter and like that. Okay, so Mr. Erwin want to ask some question.
So what I'm getting from you is that this would be the first time of you doing this thing, right, to model what is sediment is doing inside of the basin, right? Therefore, your challenge would be to determine the time when to stop, right? When to stop, because you cannot keep adding more complexity or changing any parameters, right? Just to run the model, because the model always run. The model always run. So, do you think you have any big picture of when do you think you need to stop doing the experiment and try to make sense of the results, right? Because I googled several times and I see many people doing the fairly same thing, right? Doing modeling, but they don't have something to prove it on the field as well, right? But they finish their PhD, right? So I think you also need to follow or try to learn about other people doing this kind of research and still get to finish their PhD. Right? So my question, coming back to my question, do you think you have any sign of indication on where to stop and try to make sense of the results of the model? Thank you, Pak Epo. Okay, thank you very much for the questions. Yeah, it is very challenging. Well, actually, I have my discussion in philosophy class talking about my research plan and everything else. And generally, the same questions comes out also. So when are you going to stop? Which parameter are you going to test? So we have to define the research boundary, yeah. And for my research, for my PhD, I think the research will be bounded by two things. First, I'm trying to test whether the algorithm works following the physical process. Like if it's doing the uniaxial or triaxial compression test, does it form the fractures? Does it form the fractures or not? And if it does form the fractures, what about the angle? Was it follow the real criterion that being published anywhere or not? If it does follow the criterion and it follow the physics really good, then we can step out to the basin by using the same exact parameter. So the parameter will be determined by using the first stage, yeah, the what is it one? The testing stage, yeah, and then once we're happy with that, then we continue to the basin scale or maybe to the sandbox scale. Does it answer the questions? Yeah, of course. Oh, yeah. Okay. The other thing is that they are maybe Pa Benjamin also have the same side about, you know, when we're trying to doing for modeling, we are not trying to replicate what we have in the basin exactly, yeah, Pa, but we try to capture the uncertainty, yeah, in the basin, because we do this exactly the same setup for the experiment. We try to compress it or extend it. We have the faults, we have the same angle, but somehow internally it's a kind of different. The timing of the fault, sometimes we have back thrust, sometimes we don't, things like that. Yeah, maybe this kind of research try to convince people also that we're trying to in the for modeling, we try to, like, I don't know, maybe talking about uncertainty, something like that. Maybe Bapak give a little bit of insight.
Okay, thank you very much for your presentation, Epo. First of all, I would like to say congratulations that you were able to at least generate something that maybe most of us didn't realize that it will be possible to see this in reality. I've been working for finite element for many times, but in the different situations. But in the sandbox modelings, I was trying to do the same thing for my previous candidate, but he wasn't able to do it in his dissertation. Now you are in the starting point, which is basically 25% of the start. You already there now, so you need another 75%. That's answer Pak Erwin question. So this is just the beginning, because modeling can be nothing, meaningless, but the way you models have to be controlled. That's why we're talking about forward modelings. Is something that we want to create to predict what is happened. So for geology, forward modeling is just a knowledge which is basically loose. We don't have anything, because geology is the principle, is the present is the key to the past, right? So it's not a forward modeling. Engineers do a forward modeling. So, but we can to test your idea. But the important thing, the technical issue now seems to be in control by you now. So it's just matter of setting the goal for the tool, how much the test is tool. I don't know about the scale there. I don't know about the times. Could be take 1 month maybe to generate scale. So a computer done, but everything you have the challenge. But I have to congratulate that you be able to see that. I see the models of the shortening issue, that the transport system, which is developed at least develops, but same thing. So the next one is just really took the same set like Pa Erwin mentioned, that when we were to stop, is the only things you can do is doing duplication or different type of modeling. So you can do your sandbox in the same setting as you do in your finite. But the problem, the issue is the finite difference is more flexible than the sandbox. Sandbox is just only 4 parameters that we can lock in sandbox. The rest of them is uncertainty. But in for modeling in the DMs, you can many physical properties you can do. So it will be better actually. But the problem is, like if I ever said, we don't know this is true or not, because since this is a forward modeling, you always mention that I don't know. That's why the problem is. So that's the main sandbox doing the same thing. So the result of the sandbox being matched by what we seen in the natural, right? Or crop, seismic section, or basin deformation. So we can do the same thing in this one too. For instance, we have to quantify it. For instance, 25% shortening, 30% extension, for instance, or elevated 100-meter mountains or something. So this type of issue, test it, and then if you match the quantified of the geometry, at least you reach the goal. And then the second part, the deformation. For instance, how many faults to create in your finite difference compared to how many faults to create in the sandbox with the same amount of shortening. If you can match it, sandbox with the finite elements or finite difference models, at least you can be able to say that this is a correct direction, or this is the correct parameter. I know that numerical model is much more open. Yeah, so many parameters, so it will be even more interesting to answer than the sandbox modeling, which is lots of things that sandbox cannot do in the form of deformation. but this one is open. So yeah, keep continue and then doing more. But that's the right question from you have to be able to set the goal, which one you want to models, and then when you reach that will be your stop point to writing a dissertation or whatever. Okay, that's all for me.
Thank you very much, Pak Benjamin, for the answer. Okay, thank you. And next we have some question in Zoom meeting. We have Kiflan, which raised hand. So Kiflan, please tell me about your question. Tell us. Okay, you can on mic now. Okay, thank you.
Okay, thank you for this presentation, Pak Epo. I'm Kiflan. I want to ask you. I want to ask you about. Can we use this method in mineral deposits exploration? And if yes, please can you tell me about what data we need? Like, is it geological mapping data or drilling data or etc.? Because for me, this method is interesting. I also currently learning about machine learning modeling in geology, especially for mineral deposits. Thank you.
For this kind of methods, unfortunately, there are a little bit of gap in understanding for people that doing for modeling. So it's quite different with geostatistical modeling, where we have the data and then we spread the data. We spread the model according to data. So it's like something what we call data-driven model. This one is kind of different. We cannot use the data to create the model just like that. For example, like if we have, for example, like try to make a analogy with when we are trying to create a reservoir modeling, yeah, in 3D. We have the channel over here, channel over there, something like that. So we know according to the well data, we have the channel over here and over there. But when try to doing for modeling, it is impossible for us to like match the result 100% with the well, because this is process based. I think this kind of same also with the things that you mentioned about when we try to for modeling mineral deposits. We are not using the field data, we just create the initial condition. For mineral deposition, for example, like the initial condition, maybe the host rock, yeah? We have the host rock, the property of the host rock, for example, like the type of the host rock, amount of the fractures, and then thickness, temperature, the pressure, something like that. That kind of initial parameters that that will be processed during the forward modeling and allow us to, like let the forward modeling spread the minerals all around the boundary area, like that. I think the same things also for the hydrology, Pak Erwin. Maybe Pak Erwin also familiar with simulate how the system in the how the river flowing from the mountains to the sea, and it can also be for model. And what we doing is like just let the computer do, and then we compare the final result. We cannot put initially like it have to be river in here and in there and something like that. We cannot. That we can do is just like compare the final result, whether the result from the final from the forward modeling and the reality, does it comparable? Does it looks the same? Does the channel looks have the same properties like the meandering, the shape, and the depth, the volumetric of water is all the same. So it's kind of different approach with geostatistical distribution modeling.
Okay, thank you for your explanation, Mr. Epo.
Thank you, Kifyan, for your questions. Okay, thank you. And in the chat, we have some question too. For the first is from Sir Agus Suprihatin. Isn't forward modeling in geology has determined it in geophysics? I mean, it can be described by geophysics. How the response? Yeah, basically there are geophysics. There have their own meaning in forward modeling. So in geophysics, what they mean by geophysical forward is try to um, simulate the reflectivity of the wave propagates through the earth by creating the synthetic earth layer. So if we have synthetic earth layer, then we have acoustic impedance layer, yeah? And then we can convolve the wavelet equations through the boundary layer. Then we have synthetic seismic. So what does the geophysicists do when they're trying to forward modeling is try to forward modeling the seismic process, not the geological process. They are trying to forward modeling the gravity, for example. We have the gravity map, and then the gravity map is the final product, and then we can create a synthetic gravity map by recreating the geology. That's what we call the forward modeling in geophysics. But in geology, it's kind of different. We look at the process instead of the signal propagation or gravity or something like that. Yeah, that's kind of confusing at the beginning, but I think we need to define again. There are dichotomy, whether is it for modeling in geophysics and for modeling in geology. Sometimes geology also use for modeling in geophysics to do for modeling in geology, so a little bit more complexity.
Okay, enough clearly. Okay, from Mas Agus. And once again from Adiba. Thank you, Pak Epo, for the very insightful presentation. Just a short question. The geometry-based forward model is very interesting as it's more of a shortcut, but what was the significance of having the same area on each boundary or initial condition? And is it applicable for anything other than clastic deposition? Okay.
From result also, actually, as I mentioned before, the area has to be the same. In reality, you can
Okay, enough clearly. That's the answer. Kayak jawabannya kayak dia lagi muji.
Okay, so the geometrical base is quite promising because, as I mentioned before, the area have to be the same for each step. But actually, you can change as we can know that the sedimentation rate might change along with tectonic process in the hinterland. If we have heavy active tectonic in the hinterland, then we have a lot of sediment supply, and that kind of thing also can be modeled using this kind of forward modeling geometrical base. And guys, can it be also implemented in other than plastic, maybe carbonates? Yeah, sure. If you look at the papers that presented by Peter Burgess, they are doing the same kind of things. Maybe not. Maybe they are much more advanced. They are doing 3D modeling, and they are looking for student master degree and doctoral degree, and then doing for modeling in carbonates at the moment. Their software is called CAP, like kucing, yeah, cat, and you can use it, I think, for open source, but I don't think it is not like very easy to use open source that you need to a little bit capoeira to do it.
Okay, how Adiba about the answer? Okay, thank you, Mr. Epo. Okay, we have maybe about 20 minutes again. So if you have any discussion again about this topic or something like that, we will have time. Okay, Mr. Mirzam.
Maybe I have a similar question with Bu Emi. As we are petrologists, is it possible, Mas Epo, to put some or several parameter in one particle? For example, if we can use forward modeling for predicting biogenetic stages in siliciclastic environment, for example, is it possible if we put shape of the grain and then density, hardness, what else for me, fabric, sorting, and etc. Is it possible? I mean, if it is possible, it is very good for us because we work in the detail scale within one layer. Your example is very large scale related to the on its development, and then in the basin scale.
Okay, thank you for the questions. Well, actually, when I present the poster in Houston 2023, I also mentioned that using this kind of methods, yeah, particle-based model DEM or something like that, it is possible for us to give thermal parameters in it. And because we have the thermal and then we have time, then we will be able to convert time temperature index from each particle. And as we can see, time temperature index can be converted into maturity, for example, for source rock, and for the grain of the reservoir, we can also predict the genetic process. And during the modeling, actually, we can also change the parameters of the grain because of certain condition. For example, initially, the grain size is like 2 pixels. During the deposition, if it reached the thermal maturity certain percent or certain numbers, it will shrink the size, but the mass remaining the same. Once it shrinks, it will affect everything above that. So we can also model the basin shrinkage during this kind of methods. And when tadi Pak Mirzam also mentioned about the small scale. It is possible for us to modeling the small scale. Well, it is very tricky. For example, like can we really model the sedimentation? Yeah, for example, if we have a reservoir, it consists of sandstones. Can we simulate how the mineral grows over the coating of the grain? It is possible. However, we need to understand the physics. Not only physics, I think also the chemistry. Yeah, the chemistry between the grain, the water, the temperature, and everything else, and also the reaction time between the crystal that were going to be formed, the temperature and the saturation of the water. For example, like you know that in the elementary of chemistry, we understand that the reaction is like what is it? Keseimbangan, yeah. Reaction is not one way, but also is on the other round. And that kind of concept we have to hold in order for us to able to model the precipitation of mineral in the reservoir. It is possible, but yeah, it's a little bit more complex because we need to involve also chemistry. So it's like physiochemistry kind of things. It is possible, Pak. Jadi I think there are need more people to learn about it.
Okay, I think enough for our discussion. And then, okay.
Thank you. Talk genesis, for example, of processes happen on that diagenetic. So you mentioned that we can also formulate maybe about how it works, the water, I mean the fluid at the same time, and about, and maybe also you have mentioned about the pressure. So here we can compaction. I don't know. Yeah, I mean the compaction during diagenesis. Is that possible? And again, the autogenesis process, because you mentioned about the fluid interaction between the fluid and the solid phase. So we can calculate maybe, or just predict, for example, the minerals, for example, talking about the minerals, the primary olefin, for example, the temperature is about 1100. So maybe we can, we can predict if we are talking about sedimentary, so the calcite or the, yeah. So maybe we can the temperatures in it. By comparing, the textbook mentioned that the calcite is the temperature is about 6 degrees. Well, I'm just thinking maybe we can make it. Maybe we can make it. I don't know. But it's maybe, or maybe, then deposit formation, deposit, so and so. As long as we know say the parameter, the temperature, the stress, or what else, we can select the things. Okay, I think that's enough.
Okay, thank you. Thank you for okay. So this is the end of our discussion, and I will to thank you for Mr. Epo, and for the before is from Yandex company to talk about our future geological modeling. Okay, so this is the homework for our activity for student like us to think about the future of geology, include the geological modeling, and then maybe we have to do some kind of research like this, because this is to make the other modeling, and then this is maybe different from the other modeling that have been developed by the old people. Okay, so I will thank you about, okay.
Well, I asked Mr. Muzam before whether is it possible for me to invite students. Well, actually, it is possible, and I would like to welcome any undergraduate student or master degree student to collaborate to do these things. Maybe we can create something in the future, yeah? So if you want to test us about this, then we can talk about it. Thank you.
Okay, thank you, Mr. Epo. So I will return the forum to Alia to contain the memento giving and the closing.
Okay, thank you from Fitra from moderator. Okay, for today for Mas Mirzam, time and place, welcome to forward memento from Mas Epo.
Mas Epo, on behalf of our department, would like to thank for your inspiring talk and also for a good example for our student, for master and doctoral student. Please, you should follow Epo to give your progress about your research every Friday. Don't forget. Once again, thank you very much, Mas Epo.
Okay, thank you so much for Mas Epo and to commentary for today. Okay, we would like to thank you the audience and Mas Agea from the extraordinary and enthusiast from the start and to the end from the SEMAT X Kopi Sore Alumni Yandex Special Presentation Volcanic as Distribution Modeling. But from me and all other commit members, now it's time to part. Mungkin ada sedikit pantun ya. Oke, dari Irian banyak cendrawasih. Roti menggembang diberi ragi. Cukup sekian dan terima kasih. Semoga esok berjumpa lagi. Oke, mungkin untuk para partisipan di Zoom